We begin with the Bohr model of the atom, where an electron of charge e and mass m orbits a nucleus at a radius r with a constant velocity v. This movement creates a tiny current loop. Because the electron is a moving charge, it generates an electric current. The current I is defined as the charge e divided by the orbital period t. We calculate t by dividing the circumference 2r by the velocity of v. A current loop creates a magnetic dipole moment, denoted by the Greek letter mu. It is calculated as the product of the current I and the area enclosed by the orbital path. The area of our circular orbit is simply pi times r squared. By substituting our previous expressions for current and area, we find that the magnetic moment equals E times v times r, all divided by 2. Now we look at the classical orbital angular momentum L. For a particle in a circular path, L is the product of mass m, velocity v, and radius r. Note that L and mu point in opposite directions due to the negative charge of the electron. By relating the magnetic moment to the angular momentum, we derive the gyromagnetic ratio. We see that mu is equal to the charge E divided by twice the mass m, multiplied by the angular momentum L. Niels Bohr postulated that angular momentum is quantized. It can only exist in integer multiples of the reduced Planck's constant, h bar. This is a fundamental bridge between classical and quantum mechanics. When we substitute the fundamental unit of angular momentum into our magnetic moment equation, we define a new physical constant, the Bohr magneton, symbolized as mu b. It represents the natural unit for expressing magnetic moments. By plugging in the known values for the elementary charge, the reduced Planck's constant, and the mass of an electron, we find that the Bohr magneton is approximately 9.274 times 10 to the power of negative 24 joules per Tesla. In vector form, the magnetic moment is proportional to the angular momentum vector, but points in the opposite direction. This proportionality constant, gamma, is the magnetogyric ratio for the orbital motion. To summarize, the electron's orbital motion creates a current loop, which possesses a magnetic moment. Applying quantum constraints to the angular momentum leads us directly to the Bohr magneton as the fundamental scale of atomic magnetism. The Bohr magneton remains a cornerstone in the study of atomic physics and magnetism. This derivation illustrates how classical mechanics and quantum theory converge to describe the behavior of electrons. Generated by Vision Solve AI.